Hello, 121 workshop students. I thought I would go ahead and make another video related to the falling chain on a scale. I say another one because this question was asked during Friday's Zoom. So if you go back and look at the email I sent out, you'll see that that question was asked. I spent about an hour on it, and I don't want to necessarily redo the whole problem because I think we covered that problem pretty good. But I've just got a number of questions really kind of about the physics of what's going on. So I thought I would expand a little bit on this problem, not necessarily do the problem, although guess I'll end up doing the problem, or at least parts of the problem along the way. But there's a couple of factual statements or given statements in this problem that you could just accept them as they are given and then solve the problem. And that's probably the intent of this problem. But there's a lot of important physics buried in them, and I could tell a lot of people are kind of really trying to get at the understanding, and there's like 1, 2, 3, 4, 5 equations here that I think would be helpful for me to expand on. So I'll start this way. Let me start with something you've already learned and you already know. We learned that F equals ma. Now I guess technically it's net force equals ma. And I guess I'd describe it this way. Let's say you had a bucket of water, and that bucket of water then was accelerating. All right, so you have a certain mass in the bucket, and it's accelerating. And if you just ask this just simple question, nothing else around, you're not on the Earth, you're in outer space somewhere, and you just ask yourself, how much force is needed for this acceleration of A? And this is where Newton's second law would come in. You would say, okay, well, we have a certain mass to the bucket, okay, and it has a certain acceleration, okay, and you multiply the two together, and that's how much force you get. And that's what we've been doing up to this point. I should add that up until this point, our objects were just really point objects. And they always had the same mass. Because here is why I picked a bucket of water. Let's say that in addition to accelerating, okay, there is water being added into the bucket. How much force would it take? So, in other words, you're not just taking the mass at that moment and accelerating, but there's another piece. There's more to it. In fact, you could kind of think of it this way, that if this little added piece of mass we call delta M, we might say something to this effect, that not only do we have to apply a force that is accelerating the mass that is already in the bucket, but then the added mass has to, of course, then build up to the speed that the bucket already has, let alone accelerate in the bucket. And that's what I'm getting at here. There's really kind of a second piece. You might say there's a second piece missing, because our F equals ma was really only valid when we had objects that had a constant mass. And that's what I'm trying to explain here. In fact, what I'm trying to show here is that force is really better written as the change in momentum, because momentum is a product of two things we know, and using the product rule from our calculus, we would have the first times the derivative of the second, plus the second times the derivative of the first. See, and this really is this second piece. And so better than F equals MA is F equals dP dt. And, of course, if the mass is a constant, and so come back over here, if mass is a constant, you would say this dm dt is 0 if mass is a constant. And that would go away, and you would just get ma. And so what I'm trying to kind of explain is you've had some physics. Now we're going on to what I'll call more advanced physics, where we have, up to this point, just thought of our objects as point objects, and they have a constant mass. And that this term then is ignored when we write it as dP dt. And I'm trying to say that really would be this second piece. And so back to this water bucket here. Now, so how much force would I need to make this bucket go forward? Again, you might do it something like this. You might say, well, there would be this MA piece. That is the obvious one. That's just the mass in the bucket, and you're accelerating it along. But then there would be an additional piece because you have to give momentum to this water. Let's say the water was just kind of sitting by itself on the side. You're essentially putting the water in the bucket, so you got to get that water building up to the speed of v. In other words, you would have to accelerate this chunk of water. So if you let me call this chunk of water dm, you might say, well, the additional force would be this small amount of water I add, plus the change in velocity. Divided by time. Actually, maybe I should have taken a step before that. Maybe I would write this as ma again. And so what I'm really saying back here is in this equation here, I would have the ma for the original mass, but I would also have an additional ma for the fact that I've got to take water that's not moving and then get it moving to that same speed before then the whole thing can have more mass and to accelerate on. And that's what I'm trying to say this is. So this second little ma would really be the small amount of mass I add, delta m, times its acceleration, which is the change in velocity over the time during that small interval. Now, if we do this kind of real quickly, or we do it with a small amount of mass, so we kind of imagine we're continuously adding mass to our water bucket, maybe we would write it as this. If we think of a little bit of water we're adding at starting at 0 speed, we can ignore that. And so we'll just call v the final speed. And then we can rearrange this to a dm dt, which we might call this then the rate at which you're adding mass. I mean, in the limit, that would be dm dt v. See, this is that term that I claim we normally, or at least up to this point in the semester, have been neglecting. This is the term we've been ignoring. So let me say it again. The best way to write force is dP dt, because momentum is made up of two things, and it is possible that both of those things change. See, the first term would be the m dv dt, and the second term then would be a v times dm dt. And I'm trying to give you a conceptual and a physical picture of this second term, because we so often have just focused on the first term. The first term is ma. And so again, coming back to this water bucket, this would be the amount of force to take the mass that's already in the bucket and start to accelerate it. But if at the same time you are taking water from the outside world and adding it to the bucket, you've got to get that small amount of water that you've added, and how much? Well, it depends, on what the rate is that you're adding it. But you got to build it up to this speed that's in the bucket. Then, of course, you would begin to accelerate it. So at that particular moment, I would say you really need two forces. You need the MA force. That's the force to accelerate the bucket of water. But you also need this additional force. I often refer to this as the impact force. This is the force needed to then, when you impact it on here, when you put it in, when you add it to your object, you got to get that up and going too. And that's what that number is. And so this would be Vm dm dt. So anytime you have a more complicated problem where not only is the object accelerating, but the object is changing its mass as it accelerates, the total force is made of those two pieces. So I'm hoping this kind of helps to kind of think of it as two pieces, the mass that's already there, and then the little bit we're going to be adding, because that's how I would kind of do this chain problem here. And so I've gotten, quite a few questions on the chain and the equations that are here, particularly the equation that is listed as, number 3. Where in the world did that equation come from? And it's really not so obvious. But I'm going to backtrack a little bit and just go to the first equation that is obvious. The first equation is x equals 1/2 gt squared. Hopefully that one was a little more obvious, because if you take, the scale and you have a chain that is heading up here and you let it fall, you can kind of think of these links as individual pieces. And so let me just mark this link and say, okay, it fell a distance x. You might remember one of the kinematics equations we had was that x equals to initial x plus initial velocity times time plus 1/2 at squared. And that gets us back really to that must be chapter 3 of the Survey book. But if you say then this one link where I'm focusing my attention on has starting at a spot of 0, and it starts from rest and has an acceleration of g, you get exactly that equation. So that's nothing more than the free fall equations we did in chapter 3. So I get that one. And also in chapter 3 was that other equation where it said final velocity is equal to initial velocity plus acceleration times time. And so again, for this problem with the chain, if the initial velocity is 0 and the acceleration is g for the free fall, we would get the equation velocity equals gt. And so these are our two kind of fundamental equations that the author kind of gives them. The author here of this problem doesn't even list it as problem or equation 1 and 2. It just at a time t later, the length of the chain is on the table, so they just give you that equation. It is falling on the scale. The chain falls with a speed, and then again, directly gives it. But if there's any of you out there who might have been struggling where that equation came from, I thought I would start there. Again, most of my questions really have to do with the equations in number 2 and number 3, not these two. These aren't even labeled. Now, if I go on to equation number 1, again, nobody really asked me this one directly, but I'll just throw it out there. Yeah, this is the weight of the chain. This is mg. This is, well, I guess what we did in chapter 5 when you said, the net force is equal to ma. And of course, as I just kind of went through a long-winded discussion that we could have more complicated things where the mass changes. And I'm going to do that here in just a second. But if we just think of the whole chain, then the whole chain not falling on the scale, but the whole chain just dropping it, you would say it would be the mass of the whole chain. And if I just dropped it with nothing else, no scale, no air resistance, it would have an acceleration of g, and then that would be its net force, and its net force comes only from its weight. And so, again, that's hopefully an obvious equation also. The equations that aren't so obvious are really equations 2 and the big one, equation 3. So let me build up to equation 3. But equation 2 is this. Let's imagine that you have just part of the chain on the scale. So here's the scale. And the other part of the chain is still up in the air. There's two ways to tackle this. The easiest way, but it doesn't use density, so I'm going to use the next way also, because I think the density idea will help as we get into harder problems in this chapter and next. But I would say that you could do something like this. The whole weight is mg, and then I have some fraction. So call F the fraction. What fraction of the chain is actually on the scale? See, some of it's still falling. And so this is the whole length minus x. And the stuff that's on the scale is x. So I would say the fraction is x over L. How much of the chain, x, is actually on the scale compared to its whole thing? So let's say it's at a moment in time where half of it has fallen already. See, and at that moment in time, then I would say, x over L is 50%. And so the amount of weight actually on the scale would be 50%. That's 0.5 times the whole weight, mg. So that's probably the easiest way to say this is where equation 2 came from. I think another way of doing it would be to say, well, let's think of the link and add each link. In fact, let's do more than a link. Let's maybe do each atom. And so let's add atom by atom by atom and by atom until we get to the total number of atoms that are actually on the scale. So if you wanted to know the mass, and I'll say m on scale, I guess I would do something like this. Maybe I would start without calculus and say it is a summation of a bunch of delta m's, where delta m is each little piece that you are adding together. And in my case, I'm going to think of it as each atom. And so maybe this chain is made out of steel, which is mostly iron. So I would say this is iron atom plus 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 iron atom until I get all the iron atoms that are on the scale. Not all of them that are in the chain, but all of them that are on the scale. And then I would have them. Now, here's where my knowledge of calculus is going to come into play. I'm going to take and make these little chunks of mass smaller and smaller and smaller. I suppose you could argue that I really can't get smaller than the atom. But if you could think of this as a continuous piece, you could make it, a piece of the atom, like just the nucleus of the atom, or the piece of that. It's half of iron, and iron is what, atomic number 26, I believe, so 26 protons. So maybe you could even break it smaller into the protons, and so it's the first proton plus the second proton plus the third proton, and plus all the neutrons, plus all the electrons. Anyways, I hope I'm not being too silly here, but I do want to show you that you want to think of this as chopping it into a lot of little tiny pieces and then use the definition of an integration. And so a good skill to develop is this step. How do I go from adding a bunch of things, and in this case an infinite number of tiny things, into my calculus? Because I know you've learned calculus in your calculus class, but sometimes the hard part of physics is knowing that you're supposed to actually use the calculus. And so I think the definition of the integral is really nice to write as a summation, because anytime you have a summation of a lot of pieces, you're probably going to switch it over to an integration. Okay. Now, watch this. Maybe I'll come to the side here, but I'm going to use this word density. And I think the first time I've used density in this class was last problem set in chapter 8. There was one with density. But I don't think density is foreign to you. It's something you learned in your previous physics class. It's mass per volume. But you probably haven't, until chapter 8 in the last homework set, really thought about density in terms of calculus. The traditional symbol for density is rho, so let me use that. But here's a nice little technique. I like to give the analogy of a chocolate bar and say, to get the density, you could take the whole mass, let me use capital M for the whole mass of the chain, and divide it by its whole length. Now, that kind of reminds me that maybe just to make it a little bit simpler, let's just think of our chain as a one-dimensional object of length instead of volume. The truth is it does have a width and a depth to it. But let's just call it mass per length. But you can also take one little link. And this is why I like the candy bar analogy, because you could take the mass of the whole candy bar and divide by the length of the candy bar. But most candy bars come in little pieces that can be broken off. So I can then take a little bit of mass, I'll call it delta M, over a little bit of length. And let me just call it dx. Usually we use the x for length. And so if I'm not talking about the whole length of the chain, I don't want to use like a delta L. In fact, with our calculus in mind, we might call that a microscopic amount, an infinitesimal amount of mass, dm, over an infinitesimal amount of length, dx. And I'm really going to take advantage of that right there, because this is where I can use it down here in my calculus. And remember, this is the mass on the scale. I would add up all the dm's. But right over here, dm could be replaced with rho, and when I bring the dx to the other side, this would be rho dx. Now, if the chain is uniform, I can pull it out. Now, let me emphasize, if that is uniform, right? You know from your calculus you can only do this step if it's a constant. And, of course, I did. But sometimes students get real careless when we start getting into particularly the next chapter. In fact, I noticed on the next problem set, there's a center of mass one, and it's got the density of a baseball bat. And if you know anything about baseball, you know that the bat gets fatter as you move out from the handle. And that so the density, the mass per length, gets bigger and bigger. Maybe not the mass per volume, because it's probably all made out of the same wood. But the mass per length gets bigger only because the diameter gets bigger. And you couldn't make this step. And so I want to emphasize why I'm making that step, and emphasize how that's going to come back into play as we move on to harder problems. Okay. Well, this makes it super easy then to do the integral, because I'm just going to do whatever is on the scale, which maybe I'll label from 0 to x. So my limits are 0 to x. So this just becomes rho x. And then if we finish this by saying that the rho, now back here, we first wrote as a microscopic amount of mass to a microscopic distance, we could do this. We could take the whole mass over the whole length. And so this is the whole mass over the whole length times x. And so sure enough, if I write it with lowercase m for total mass, and the x in front, and then the L, I get how we wrote it right here. I guess we have a G. So to get this weight, we'd have to take the mass and then multiply by G. Okay. But that is a way, and I might say a longer way than just doing the fraction. So at this point, if it's just a fraction and it's nice and uniform, I would recommend what I did. It's the quick and easy way to get equation number 2. But I wanted to go on and show you this way, especially as we lead into the next chapters where the density is not uniform. And we'd have to put in some kind of equation here and do the integral with the row, with the density inside of the integral instead of out in front. All right. Well, I hope my little sidetrack here wasn't too long. But I did want you to see that there's 2 ways of coming up with the equation that's listed in step 2. And then so x mg over L is the amount of weight that is actually on the scale. And again, probably the easiest way to think of it is this is the whole weight of the chain, and then this is the fraction that is actually on the scale. Which is why when we do the integral, we only get the fraction because we're only integrating the length of the chain that's actually on the scale. Okay. All right. Well, finally, I get to my main point that I really wanted to kind of make this video. And it really comes way back to this whole discussion and my kind of discussion about water in a bucket. Because to get the force, then, you actually have a derivative of the momentum, and the momentum is a product, so we have the product rule, and we actually have 2 pieces. And you can think of this first piece just as the acceleration of the object of fixed mass, but the second piece needs to be added because you're adding mass, and so that's like you're putting the mass into the bucket, and you got to get it going just up to that speed, let alone accelerate it, so you have additional momentum. And so both of these are change in momentum. This is a change in momentum because it's going faster, but this is a change in momentum because we're giving it more mass. And so we didn't really deal with this one until now, which is rightfully so. All of our objects had a constant mass. They were little point objects. Okay, so let's see if finally we can make a little more sense out of equation number 3. And let me see if I can kind of use this whole idea of momentum, since that's what this chapter is really based upon. Let me write that then the force, net force, say on the chain, is the derivative of the momentum. And I'll write the momentum as mv. But here's what I'm going to do to maybe kind of help understand it. Let me draw the scale with part of the chain already laying on the scale and part of the chain still extended up into the air. And let's do this. Let's just actually split the chain so that the part that's actually on the scale, let me call it M1, and the part that's still remaining up in the air as M2, so that M1 plus M2 is equal then to the total mass. And so I'm going to look at it as 2 pieces. Now, for clarity, where do I draw this line that separates the 2? Okay, I'm going to draw this line separating the 2 to be kind of the microscopic position just after the link makes impact. So in other words, as the link is hitting the scale and slowing down and eventually coming to a stop, all of that is still on chain number 2 or mass number 2, okay? once it comes to a stop and it just lays there, I'm going to say it has zero speed as it gets added to mass number 1. Okay, so that's kind of the dividing line. Okay, so again, the link, as long as it's in the air or as long as it's still moving, it is part of number 2. Once it has come to a stop, it is now added from number 2 over to number 1. And of course, then number 1 is growing in mass. Number 2 is losing in mass, although number 1's not actually moving. Now, here's why that's important. Let me take the differential of this. dm equals to dm number 1 plus dm number 2. Now, the total mass doesn't change, which, of course, really just means that there is a negative sign between how the mass in number 1 and how the mass in number 2 change. And that's not a surprise. We know that number 2 is losing mass because each link hits and now gets assigned to number 1. And so number 1 is growing in mass and number 2 is losing in mass. Now, I don't know if that's going to be real important here, but it does kind of allow me to do a little bit of calculus here and hopefully emphasize the division mark and to emphasize that the total mass of the chain doesn't change. So let me do this. Let me take this down here and write that the total mass is m1 plus m2 and whatever speed it has at that moment. Let me also then separate that into 2 pieces. So we've got m1v dt, and we've got m2v. All right. Now what I have is a problem where I've got 2 objects, and the 2 together makes the whole chain. So this is the force on the whole chain, okay? But these 2 is then the 2 pieces. But now you can see that they're changing mass. And so now you see back here why I started this whole video, it's kind of like a mini video lecture, to point out that if you have something that's not only changing its speed, but also changing its mass, you need the 2 pieces, okay? And up until this discussion about water in a bucket, all of our objects had just a fixed mass. And so we only did this term. We only did the ma. We never did the additional momentum that is needed to be given to the bucket because we're just giving it more mass. And so I need both of those. And that's what I'm trying to show you here. So I'm going to need both of these. So the first term would be, well, let me write it this way, m1 dv1 dt. And so maybe I should have put a 1 here and a 2 here, especially since number 1, as we said, was everything that's at rest. And then over here, we have this other piece, which is the moving piece. All right, but let me take the 2 pieces here from chain number 1. Okay, so it's m dv dt, and then also v times dm dt. Okay, and that would be number 1. Then over here, this right here would be m2, and then I would have the, see if I'm saying this right, dv2 dt. And then I would have then the dv, or v, number 2, and dm2 dt. Okay. And this is kind of that main point here. So maybe I should write this as net force. Okay. Where net force, of course, is all the, forces on the object here. But I wanted to kind of look here and say, all right, what do I have here? Okay. I have, in terms of this net force, gravity pulling it downward. So if we call down positive as they do in this problem, it's mg. And then you might say upward is a normal force from the scale. Okay. Okay. Now, that has to then be equal to all this stuff. All right. So let's talk about this stuff here. Okay. And this right here, this dm